Welcome back. This is the first of 3 videos on linear ordinary least squares regression. In this video, we'll cover the mathematical foundations of bivariate linear regression using ordinary least squares, or OLS. The next video will focus on interpreting linear regression models and checking their validity. For now, the main thing to remember is that OLS regression is a linear model with coefficients that can be interpreted as the change in y for a unit change in x. The third and final video in the series extends OLS regression to multiple independent variables. We won't talk much about the details of estimation as it gets pretty complicated to do by hand and we'll really only need to use computers, but adding multiple independent variables is powerful. By adding them in the same equation, you can estimate the effects of each variable, holding all others constant. But for now, let's step back and talk about how OLS regression relates to what you already should know. When our model was simple means, the master equation we used to represent one case was y equals the mean of y plus error, or x equals the mean of x plus error. Linear regression adds one or more coefficients into the model multiplied by x variables, which also then changes the value of what was a mean, that mean of y or x, to a constant term, that is the prediction when all x variables are 0. Now there are many ways to represent a linear equation. In high school math, it's often written as y equals mx plus b, or y equals a plus bx. Statisticians most often use b0 to represent the constant. You can remember it because it's the value when the x's are 0. And they use b1, b2, and so on to however many b's there are to represent the coefficient for each independent variable. Now, before we go on to estimation, I'm going to show you a scatter plot with a regression line on it and talk about the different elements of the equation. I'll post a picture in the course site that shows this whole board, which has almost everything you need to know from these 3 videos except for the assumptions, all in one spot, as well as some review from previous things. So let's take a look. Here's our board. In the center is a scatter plot, you see. Each little spot is x is study time in minutes, y is score on a test. So here's 50 points, 100 points on the test, 20, 40, 60, 80 minutes. The mean of x, that's x bar, is 40. The mean of y is 70. So the average student studied for 40 minutes and scored 70 on the test. This is the regression line. We'll talk more about that. But first, look at the pattern of data. You can see it's roughly linear between x and y. It generally follows a pretty nice line, actually. This is made up data, by the way. The regression line here is actually y equals 50 plus 0.5 times the minutes of study, or y equals 50 plus 0.5x. The next video will talk more about this, but 50 is what's called the constant, that b0, and is the value we would predict y to be if x, that is study time, is 0. 0.5 is the coefficient for the x variable of minutes of studying, and means that for every 1 minute spent studying, we predict scores to go up by half a point. So how do we get from this scatter plot to that line and that equation, other than guessing? Well, we need to know 2 things, both of which we've calculated before. First, we need to know the sum of cross products, that is, what's on the top of the covariance equation. You can see over here, variance is here, covariance is here, so it's x minus x bar times y minus y bar, and we add that up for each case, and then divide that whole sum by n minus 1, but we're not dividing this time. This top part is called the sum of cross products. If you look on the graph, I've shown some examples of x minus x bar for a case, and y minus y bar for some different cases. So for example, for this case, that's x minus x bar. This would be y minus y bar. That would be larger. So as either one gets larger, this cross product gets larger. And if either one is very small, the cross product will be small even if the other one is large. So this cross product represents the association for that case of x and y net of the means. That is, if x is higher, is y also higher, and by how much? Adding these up gives us a kind of average association. Second, we need to reach even further back to the sum of squares for x, which, instead of being the top of the covariance equation, is the top of this variance equation. It's x minus x bar times x minus x bar. We usually just write that with a square, but notice the similarity here to the cross product deviation. The difference is, here we're summing the squared deviation, so our unit is x in both, so we would take this and square it. Because we want our coefficients to be scaled by x, that is the effect of a 1 unit change in x, we need to divide our sum of cross products, this, by our sum of squared deviations for x. This represents the overall variability of the independent variable. Now, to get the coefficient, the b, or b1, for the independent variable, we simply divide the sum of cross products by the sum of squares total for x. We'll explain that total another time, but we'll just leave it there for now. Or equivalently, if we've already calculated them, mathematically it's equivalent to say that the b coefficient is equal to the covariance divided by the variance of x, or the correlation of x and y times the standard deviation of y divided by the standard deviation of x. You can see how these are all related. The difference between the first two, the sums and the covariance variance, is simply these n minus 1s, which cancel each other out, and it's just a way of controlling for sample size. And if we've done that, then to find out the constant, we can just plug in our coefficient, our b1, in this case 0.5, rearrange the equation. So if we've got y equals b0 plus b1x1, if we move the b1x1 to the other side, then it's b0 by itself equals y minus b1x1. And if we substitute the means, then we get the constant is equal to the mean of y minus the coefficient times the mean of x. So in this case, constant equals 70 minus 40 times 0.5, or minus 20, which is 50. And you see here, that's where the x intersects the y line at x equals 0, y equals 50. Now remember we said correlation was linear even though we didn't calculate a line? Here's the evidence. Not only can you calculate forward to the OLS regression coefficient from correlation and standard deviation, you can also get back to correlation in a way that looks very different. It's not on here, but it's worth knowing. First, we would need to predict the values of y for each case based on our equation. So for each case, we would plug the value of x into that. In our case, y equals 50 plus 0.5x. So if x equaled 20, then y would equal 60 in our predictions, and so on. Now, if we square each error term for our predictions from the line, for our predictions from the actual y value of that case, then we get the sum of squared error in predicting y. We already know how to calculate a sum of squared error, predicting it from just the mean, that is, the sum of squares total, like we did for x. And the difference between these two, between the total sum of squares and the sum of squares error, that is, what's not accounted for by the model, is called the model sum of squares, and it represents how much we improve our overall prediction by adding independent variables. Or more technically, it represents the variance in y explained by the model. If you divide this by the total sum of squares, it converts variance to a proportion of the total variance in y explained. This is also known as r squared, because if you were to calculate the correlation of x and y, starting from the covariance and the standard deviations, and then square it, you would get the same identical number. So normally you'll calculate any kind of a regression on a computer though. So the most important thing to take away from this is not the nitty-gritty details of how each thing is calculated, but how the quantities are related and what they mean, what are the units, and, as we'll get to more in the next video, how do you interpret it. So that's all for now. Make sure to watch the other 2 videos on regression so you don't end up thinking this is all a bunch of pointless math with no meaning. In the meantime, have a great day, and thanks for watching.